Hello, my name is Angelo, or Dim, and this is part 4 of my series on building Trust, a Terraria server in Rust. The last 3 parts are available as blog posts. I decided to make this one a video because trying to explain everything in text would be pretty damn annoying. So, what am I doing in this video? As a quick recap, here's where I'm at in making my Terraria server. At the moment, I've decompiled the Terraria server using .peek, and after many lines of Rust code, I can now connect to it using the native Terraria client. It sends tiles to the client, but trying to break a tile does nothing. This is because when the client breaks a tile, they expect the server to drop the item so that they can pick it up. Whenever the client breaks a tile, they send the packet with action 0 and target type 0. So, we must check for that first. In the packet, we also know the X and Y of the tile that the client broke. So, let's look that up in our world tile data. If we just drop an item with that tile ID, we should get the block as a dropped item back, right? Let's go ahead and broadcast this tile drop event to all our clients using tx.send. The details aren't very important. All you need to know is that when we call tx.send with a message, it encodes the message in binary and sends it to all the clients. First off, we have to give our dropped item an ID. This is because each dropped item has a unique ID identifier to determine which item it is we are talking about. This number cannot exceed 399 because a Terraria client can only handle up to 400 dropped items before it starts deleting old dropped items. We can just use 0 for now since we're testing, but later we would want to keep track of potentially all 400 dropped items. Next is the position of the dropped item. To translate between a tile's position to a position in the world, we have to multiply by 16. Terraria treats tiles as 16 in length and 16 in height. Next, we want a velocity for the item. This is what gives items in Terraria that jumpy effect when you break them. Terraria picks the X velocity to be between -3 and +3, and the Y velocity to be between -1.5 and -4. So we're going to do the same by using the Rust random crate, which produces a random float between 0 and 1 when we give it an F32. Here comes the most important part, our item ID. For now, let's just assume that the item ID is the same as the tile ID. Next is own ignore. I'm not quite sure what this does, but let's set it to false since that's what the Terraria server does. Prefix is used for any item modifiers like legendary or mystic, but we can just set it to 0 for none. Finally, stack represents the number of dropped items in a stack. We can just set this to 1 since we only have one broken block. Later on, we would want to group nearby items that are the same together since this is what the Terraria server does. Now let's go ahead and see what happens when we run it. Nice, breaking that grassy dirt block gives us dirt. Breaking the wood block gives us dirt walls. Breaking the platform gives us gold bars. And breaking dirt gives us nothing. What is happening? Well, as it turns out, Terraria gives tiles and items completely different IDs. This makes some sense because not every item is a tile. For example, a wooden sword cannot be placed, therefore it shouldn't have a tile ID. What this means for us is that we need a way of translating from a tile ID to an item ID. If we check the Terraria fandom wiki, we can confirm that. There are 2 pages, one for tile IDs and one for item IDs. Here, we can see that an iron pickaxe has item ID 1. However, tile ID 1 represents a stone block. Does this mean that by breaking a stone block, we get an iron pickaxe? It does. Let's figure out how Terraria handles this. Looking at the decompiled Terraria code, we can see that when number 10 equals 0, aka action equals 0, a method called worldgen.killTile is called. Let's go over to that method. KillTile does a bunch of things to remove the tile from the world tiles, but eventually it calls a method called killTile_dropItems to trigger the tile to drop an item. This method, killTile_dropItems, calls another method called killTile_getItemDrops. Now, this is the method we're looking for. This is the thing that is converting tile IDs to item IDs. It does some stuff up here by this if statement, but that's not that important. What I really want is the switch statement. Yeah, this switch statement. The one that's about 1600 lines long when decompiled. Could I just implement this by hand? Well, for some of them, I kinda have to because the block is pretty unique and there's no real way to automate it. However, a lot of this is really similar. This is what inspired me to write a C# to Rust converter. Now, it's not a full-blown converter, it is basically only for this switch statement. The benefit of automating most of this is that 1. In the event of a future update, I can quickly run the script again on this function to support new tiles. 2. The chance of human error is greatly reduced. I figured that by writing this by hand, I'll probably make some mistake somewhere along the 1600 lines of code. I will probably never actually find that mistake. By automating it, I feel a bit more confident in that I won't make a subtle mistake. 3. It may save time. It ended up taking me an entire day to learn to use TreeSitter and to write this converter. It took another half a day to do the unique cases by hand. I probably could have just converted the entire switch statement by hand in half a day. I guess it hasn't saved me time, but when Terraria gets more updates, I'll be able to adapt more quickly than I would have otherwise. Anyway, that's the entire motivation for this. Let's get to writing actual code. First off, I mentioned something called TreeSitter without telling you what it actually is. TreeSitter, for my purposes at least, is a parser generator tool that can build a concrete syntax tree for some given code. TreeSitter has bindings and parsers for many languages. At first, I was going to use Rust for this, but had some difficulty setting up tree parser, and the docs weren't particularly helpful. I then decided to go for Python since I enjoy writing scripts in Python anyway. In order to start using TreeSitter, I'm going to create my convert.py file. First off, we want to import TreeSitter, and from TreeSitter, we want to import the language class and the parser class. In order to install the TreeSitter bindings for Python, you of course have to run pip install tree-sitter. I already have it installed, so it doesn't really do anything. So let me go ahead and cd into my scripts directory, because now we do have TreeSitter, but TreeSitter is really just a framework for parsing languages. We need to actually get the parser, and on the TreeSitter page we can see all the languages that TreeSitter is capable of parsing. We care about C#, so let's go ahead and open up the C# link. I'll copy this git link and git clone the repository. With the repository cloned, we are now going to build a library for the language. In order to do that, we're going to call upon language.buildLibrary, and we are going to specify an output file. So I'll go ahead and specify build.so in the build folder, because this creates more than one file, so I want it to all be inside the build folder. And for the actual repo path, we're going to specify treesitter-c#. The reason this is a list is because you can have multiple languages in one library. Next up, we have to create the parser. To do this, we just instantiate the parser class, and we set the language of that class by loading the library that we just created. So we'll load it from build/build.so, since that's where we created, and the language that we want is C#. Even though the repository's name is C-#, the actual name of the compiled language is C_#. So just watch out for that when you're loading a library. Next up, let's go ahead and use our parser to actually parse something. I'm going to construct a tree from parser.parse. And from here, this method only takes a bytes object, so we have to specify bytes. For the bytes, we have to specify an encoding. I'll just use UTF-8. And inside of this, let's go ahead and write int x = 4, just so that we can see what the tree looks like. Next, we are going to walk the tree. This creates a tree cursor that makes moving around the tree really easy because it has methods like go to descendant, go to first child, go to next sibling, go to parent that we can use to traverse the tree. In order to debug the tree, we are going to use print cur.node.sExpression. What this does is it prints an S expression, which is basically just a tree that kind of looks like Lua code. Let's go ahead and run the script now to see what it'll do. So first off, it builds the library, and then it's able to parse the code, and this is the S expression of our tree. So first off, there's this global compilation unit followed by global statement. This seems to always be present in C# files. I haven't tested it for other languages. Next up, we have local declaration statement because we are declaring something here. Next up, we have variable declaration. And inside of here, we have the type of the variable, which is going to be int. And within the type sibling, we have a variable declarator, which holds a name, which is an identifier, which would be our x here, and an equals value. This just represents the equals sign, and the integer literal, which is our 4 here. Let's go ahead and see how we would actually get to that 4. So first off, we have to run cur.goToFirstChild, since we start at the compilation unit, so we want to go into the global statement. If we run that, we can see that now we are in the global statement. We have to go another layer deeper, so let's go ahead and go to first child again. We are now in the local declaration statement. Once again, we have to go another layer deeper, so let's go ahead and go to first child again. And now we are at variable declaration. If we go to first child, we'll end up in this type, so we actually want to be in the next child, or the last child. So let's go ahead and do that. Go to last child. That puts us in the variable declarator. And now we have the name and the equals value clause. So we want to go to the equals value clause, which is the last child. So let's go ahead and do that. We are in here. Now let's just go to first child in order to get that literal. First child, last name. As it turns out, it's actually an equal sign, the first child, because it represents that equal here. So in order to get around that, let's just go ahead and go to last child. Alternatively, we could also cur.go to next sibling to go to the next sibling. So let's do that. We're at the integer literal now, and we basically have it, but we're still just printing it as this s expression. We want to get the actual value of it, and in order to do that, we can do print cur.node.text. And here you go. We have a bytes object with the 4 in it. That's the basic rundown of using treesitter in Python. Now in order to turn this into like a full-on converter, there's a lot more steps. We can go ahead and get rid of these lines for now, because we still want to get past that compilation unit and that global declaration. So let's go ahead and start by putting a switch statement in here. I'm going to go to the actual Terraria source code, or at least the decompiled source code, and get the switch statement that I want to work on. It's over here. And let's just grab the first 2 cases for now. We can worry about other cases later, but for now, I'm just going to do this. With this, we can go ahead and run the script again and see that we get a much bigger s expression. We can also see the text representation of this and see that it just contains the switch statement. Something I'd like to do right here is just decode this as a UTF-8 so that the string gets printed. And as you can see, we get the full string in our console. Next thing I want to do is I want to be able to look at these many numbers in the case statements and then see that it maps to a 2. We are currently in the switch statement, and if we look at its properties, it has this value as its first child, and that represents this part right here, the thing that we are matching on. The body of the switch statement is the thing here that's surrounded by braces. Since we don't really care about what we're matching on, because we know it's always going to be tilecache.type, let's go straight to the body. In order to do that, we are on the switch statement going to go to the last child. I believe this might just give me a closing brace, but let's see. It does not. We are in the switch body, and the switch body is probably what's going to have the closing brace. So let's go ahead and go to first child within the switch body and see what that prints out. Okay, we just get that brace. So let's go to the next child, because right now we're here, but actually we want to be here. So a lot of the time things in treesitter are sort of broken up like that. You'll have the literals like this opening brace and this closing brace, and you'll also have random equal signs, and you just kind of have to traverse them. So in this case, we're currently at this open brace, but we want to get to the next child. So let's go ahead and go to next sibling. As you can see, we're currently dealing with this block here. So from here, we are going to look at each of these cases and just grab the number value out of it. So let's go ahead and look at our S expression. Within our S expression, you can see that we have a switch section. And in that switch section, we have the case switch label, another case switch label, another case switch label, and so on. So we are going to want to go through each of these children. So let's go ahead and write something to loop over the children. The way that I would go about this is just loop while the node's type is this case switch label. And then when it's no longer a case switch label, aka when we get to this expression statement, we can just exit out of that loop. So let's go ahead and cur.go to first child, and we'll see that when we do that, we just get this case 0, and it is a quick case switch label. And let's do while cur.node.type equals this case switch label. Let's go to the next child, and this will go through all of the case switch labels. Now that we're in a case switch label, let's go ahead and get this 0 here. So you can see that it's just the integer literal, which is the first child. When we get to this kind of nesting where we would have to go into the first child and then step back out of that child, this is the point where I would like to create a copy of the tree cursor so we don't mess up the position of the first tree cursor. So at this point we can do cur.copy. And that creates a tree cursor in the same spot as the previous one, but modifying this one won't modify the old one. So now that we're in this, let's go ahead and go to first child. And in the first child, let's go ahead and just print its node's text and see what that produces. As you can see, we are currently at the case. And that makes sense because the way that this is broken up is case and then integer literal and then colon. So from this first child, let's just go to the next sibling so that we can get the actual number. And as you can see, we're getting these results: 2, 109, 199, 477, 492, semicolon. We have made a very classic mistake here. So notice how these cases start at 0, but we're actually starting at 2. So the reason that we're ending up at the semicolon is because we are going to the next sibling, and then within the next loop, we're checking if the node type is case switch label. What we should do instead is put this cur.goToNextSibling at the bottom. And we essentially just had an off by 1 error. So by doing this, we'll have the right output of 0, 2, 109, 199, 477, 492, all right here. Let's go ahead and just make a list real quick so that we can store all of these numbers. And let's also go ahead and push to that list using int of c.code or c.node.text.tcode as UTF-8. And after all this is done, let's print out our numbers to see if it makes sense. There we go, we have our numbers as a list. With our numbers now in this list form, we know what we are matching on, but we also want to know what it's mapping to. So we get to this expression statement, as you can see right here, after we've gone over all the items and the assignment expression. So that is what we have here. We have an assignment expression. We don't care about the identifier. As a matter of fact, we do sort of care about the identifier. We can just make a quick assertion that the identifier is drop item in order to make sure we're not accidentally working on a case that isn't really in this format. And the right is what we care about the most though, the integer literal. So let's go ahead and start doing that. Like I said before, when I'm entering nodes like this, I like to make a copy. So let me go ahead and make a copy right here. Within this copy, let's go ahead and go to the first child, and let's just print out the results of that. We are still printing cur. We want to print C now. As you can see, we have this assignment expression, the left identifier. So let's just see what the left identifier is by going to the first child. Right there, you can see that it's drop item. So what I want to do here is just write a quick assertion that the c.node.text equals this drop item. And remember that text is a bytes object, so we have to create a bytes literal right here. The assertion is good. And now let's go to the sibling of this identifier. We have the assignment operator, so let's go to the next sibling because we were here at drop item and then we went to the next sibling which took us here, and now we want to get to here. So let's go one more time doing next sibling. And now we're at 2. This is exactly what we want. So let's go ahead and create a result variable. And the result will be this node.text.decode, and let's just make it an int. Making it an int isn't totally necessary, it's just something I feel like doing because it asserts that this is in fact an int. Also, it's good to write a lot of assertions whenever you're doing this sort of tree parser stuff and walking a tree, because as soon as something is out of whack, you'll immediately get an assertion. And the more assertions you have, the easier you'll be able to pinpoint what is causing the error. Next up, let's go ahead and convert this to Rust. If you're not familiar with Rust match statements, I'll just show you them real quick. Rust match statements let you match on a specific variable, and as you can see here, we can match on several values by putting a pipe in between all of them, and the equals will just represent what this maps to. So here we would join our numbers in the case statement with a pipe in the middle, and the result would be that result variable we have. And of course we have to handle the default case here. We could just make this return -1 or 0. Let's go ahead and start generating our Rust code. So first off, we are going to create that match, and here is the point where we kind of have to know the context of the application. So in my case, we're going to be creating this as a method on tiles. So it is going to impl on tiles, which means that self.id will be the tiles ID. So let's just go ahead and match on self.id, but this is heavily dependent on your context. And at the end of everything, we are just going to want to put in a backslash and a closing brace. Let's go ahead and print out our Rust code to see what it looks like. As expected, there's nothing yet. Another thing that we're going to want to append is the default case. So I'll just go ahead and do that right now by doing /n underscore, and then we'll map this to 0. You'll notice that this is not properly indented, so let me just go ahead and throw a tab in there. With that done, let's do the actual numbers and the result part. In order to add the numbers as one of the match arms for this match statement, we're going to use an f string, and it will be a new line and indented, much like this one. And at this point, we are going to want to join all of our numbers by a pipe. And in Python, you unfortunately cannot join just integers together, so you're going to have to map them to a string and then the thing that you want to join on. And then you can call join on that iterator return by map. And now we are going to want to go ahead and write the value that this maps to, and that is just our result variable here. So let's go ahead and put result and the comma and see what that gives us. As you can see, 0, 2, 109, blah, 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 that all maps to 2, which is great. That is exactly what we're doing here. Next up is this one. So you'll notice that the way I've written this, it's just going into the first block and that's it. So what we're going to want to do is step out of this block so that we can then go to the next sibling. Ideally, you would use a cursor copy here, but because I've already written the code this way, I'll just go ahead and step out of this block using cur.goToParent. Also, we'd want to write this Rust code way up here because all of the iterations of this should continue adding on to this match statement. Let's go ahead and comment out this print statement, and to know what we are exactly iterating over, right here, when we do cur.goToNextSibling, let's just print out cur.node.sExpression. As you can see, we have this switch section. So we are focused on switch sections. While cur.node.type equals switch section, we are going to continue this loop. And in this loop, on every iteration, we are stepping into the first child, so we have to make sure that we step out of that child. And also this should be in the block. At the end here, cur.goToParent and cur.goToNextSibling, so that we can go to the next switch block. Running that, we get a pretty good result. As you can see, it maps 0, 2, and so on onto 2, and 1 onto 3. This is more or less how you use tree sitter in Python. Now, in order to go from this to this whole file, it takes a couple more steps. In fact, I define a walk switch method here, which is a recursive method, and this is pretty ugly. I just kept adding on more parameters as I needed more in recursive calls. But anyway, all of this is basically just an extension of this. If you can understand this much, you can eventually get to this point. This is just more code and very, very spaghetti-like on top of it. Something you'll notice here is that I'm constantly calling this function called s. For some reason, whenever I tried doing .text on any of the nodes, it just didn't give me anything. I'm not sure what was causing that bug, but my way around it was to create this method s, which would just take the node and then from the source use the start byte and the end byte of the node and decode that. And eventually, once I'd finished all of that, I was able to convert this switch statement into this. As you can see, we have our well-known 0, 2, 109, blah, 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 and a bunch of other things. There were a lot of one-off cases that I simply implemented by hand, and the full list is right here. So for example, 3. I implemented this one by hand. 5, 596, 616, 634, those were implemented by hand. Or to be implemented. I don't know. Anyway, I believe this script saved me a lot of time, and it taught me about TreeSitter, which I didn't even know existed at one point. One of the very kind people at Recurse Center, his name's Alexander, he taught me about this thing because for some time I was trying to write my own parser in Python for C#, and it was a very painful process, and I would not recommend it. So if you need to parse a syntax, just use TreeSitter. TreeSitter is really good. Anyway, that just about covers it. I hope you've gained some knowledge about TreeSitter. I hope that you actually put it into practice and are able to create something using TreeSitter. And let me know if you do, because I would really be interested to see what other applications people have for this kind of thing. But yeah, that's pretty much it. Thank you so much for watching, and see you next time.